We're going to go ahead and get started. Um, First thing, I want to just say a couple things before we actually get into class. There is a specific kind of procedure for this class. Okay, and I explained this day one, and I think I've said it a couple other times in different classes. You check into on campus, you come here, we do the lecture, and then after that, I'll give you time to work on your homework where I'm available on Teams in order for help. Okay. Um, on large part, that last part is not happening. Okay. So a lot of people are posting none uh, to do you have any questions over last night's homework? Okay. Which is fine if there are none. But one, if you haven't attempted it, that's like not okay. And two, if you have attempted it for just a couple of problems, maybe one or two, and then just given up after that and not ask me for any help, that's also a problem. Okay. So I'm giving time after this every class period, and it might be shorter on some days. It might be 30 minutes one day, it might be 20 minutes the other, and we might run out of time on other days. That has never happened before, though. Okay. I give people time in teams to work and also be able to ask me questions so I can help you kind of on a more individual basis. Okay. So if you are not showing up to teams, to the meetings in teams after, uh, you're doing about a half of what I'm really asking you to do. So yeah, there's the lecture where you can just sit and watch me do problems and kind of explain concepts. But if you only do that, you're really not getting a whole lot out of it. Okay. Um, so again, when I see people answer none and they haven't attempted it yet, or just complain in the discussion board, it's a little bit frustrating, especially if they haven't even attempted um, the homework. Okay, so that needs to change. I realize there's not a whole lot of class days left. We will be having one more day of content. Um, I'll cover, well, maybe we might be like a half more day of content. Okay, and then I'll get you prepared for the exam. The exam will probably be kind of like the matrix test was. Um, I don't think you guys are ready for any type of project, and given people's kind of participation and all this stuff, I don't think that's smart either. Okay, so it'll probably be more like a traditional exam. It'll just be over this content. I'll give you kind of a 2 hour window to do it. You'll have to, take a picture of it, submit it to me, and then I'll grade that, and that'll be your final. Okay. Uh, I would have liked to have done a project if we had a little bit more time, or it wasn't in this context. I think we would have gotten to probability and we could have done some pretty cool stuff. But given the situation, I don't. It's not reasonable. Okay, so we'll cover today. We might cover just a little bit more in the next class period, and then we'll start reviewing. Okay. So all that being said, I want to give people like another minute or two just to like actually ask questions. So if you do have a question that you're unsure of and you didn't maybe put it in the discussion board, why don't you go ahead and do that? Okay. And I don't mean I can't get past 90, because quite frankly, if you're at 90 or in the 80s, you know it pretty well. Okay. But if you have a specific question, I'm going to give you time. Go to your email. You can screenshot something. You can send it to me, whatever. But I want to give people time to actually do that and take advantage of it. So I'll give you another 2 or 3 minutes, and then we'll actually get started. So I haven't gotten any emails or anything new on the discussion board. Okay, if you do have questions later, we can talk about it in teams. But for now, I want to kind of cover one more thing that is kind of a tangent, not a tangent. It's a part of all of this sum of a finite geometric sequence. Okay, except it's an infinite geometric sequence. So really quickly, what we went over last class is the sum of a finite geometric sequence, which is this equation that you see up on your screen. Okay, it's not, there's nothing like super hard about it. It's just pulling out numbers and then plugging them into an equation. Okay, so the sum of a finite geometric sequence from 1 all the way up until n is equal to the first term times 1 minus your common ratio to the nth power over 1 minus your common ratio. That's it. It's just plugging numbers into an equation and getting a number out. Okay, so your homework was W9, which was really distinguishing between an arithmetic sequence and a geometric sequence. Okay, so if something had a common ratio where the ratio between two sequential terms was constant, then it's geometric. If the sequence had a common difference where the difference between two sequential terms was constant, then it was arithmetic. Okay, there were some cases where both of them were the case. Okay, so if the sequence was just a constant over and over again, then the ratio between two sequential terms, right, is just 1, right? Anything divided by itself is just 1. And then it's also arithmetic because you're just adding 0 over and over again. Okay, and again, if something makes sense like right now that didn't make sense when you were doing it, or you have questions and you can fix them later, I'm trying to be as lenient as I can with due dates on homework, so I'm waiting a couple of days before I actually put them in. So if you want to fix something, go ahead and do it. All right. So that was W9. W12 was largely this example. Okay. Again, sometimes it's harder. Sometimes it doesn't necessarily start at I equals 1. And we have to be careful about how many terms we're actually adding. Okay. But it was generally this equation, pulling out numbers from it and plugging them in. Okay. So since there are no questions about that, or at least I haven't seen any, I want to cover one more thing. So this is just one more equation. I'll do a couple of examples, and then I'll let you guys get to work. Okay, and that example, or that new concept, is the sum of an infinite geometric sequence. Okay, so a finite geometric sequence is a sequence of numbers that stops somewhere. An infinite geometric sequence just keeps going, right? So there's a first term, a second term, a third term, a fourth term, but then it goes on forever. And we can sum that sequence if our common ratio is less than 1. So if we multiply any number by something between 0 and 1, it gets smaller, right? So if we do that continuously, it will what we call converge to a specific number. Okay? So if the absolute value of r is less than 1, our sequence converges. If it's greater than 1, then the sequence diverges. Okay, but this equation that we're about to go over only happens when the series converges, so r is less than 1. Okay, so when that's the case, when the common ratio is less than 1, we can sum that sequence by dividing our first term by 1 minus the common ratio. So then this equation, again, is something that's pretty important. So if you have this out in front of you, it really shouldn't be that difficult to do, okay? All right. So for example, if we have this sum, and I'll move this up just a little bit. If we have the sum from n is equal to 0 all the way up until infinity, so this is an infinite geometric sequence of 4 times 0.6 to the nth power, there are two things that we need. We need the first term and the common ratio. Okay, the common ratio is always going to be the thing with the exponent attached to it. So r, in this case, is 0.6. In order to get the first term, we just plug in 1 into this sequence. So it's 4 times 0.6 to the 0 power, right? Not 1, it's the first term that we see. Okay, which is n is equal to 0. And when we do that, we just get 4. All right, so usually your first term is the thing without the exponent attached to it. Okay, and then once we have both of those numbers, we plug it into this equation, and we get a number. All right, so if we do that, we get the sum is equal to our first term over 1 minus our common ratio, which is 0.6. When we plug that into a calculator, 4 divided by, and then I put parentheses around the denominator, 1 minus 0.6. So we get 10. Okay, so this infinite sequence with an infinite number of terms converges to 10. So the sum of an infinite number of things is just 10. Okay, questions about that example? Okay, so this small example for the most part is your homework. I do want to go over one or two different types of examples just so you see them because they do pop up. All right, so say I want to find the sum of the infinite geometric sequence of the sequence given, right? So we go from 10 to 2 to 2/5 to 2 over 25. A couple things we need to take from this. We need the first term, which is really just the first term that we see. And we also need a common ratio. And because we know that it's a geometric sequence, we can just take the ratio of two sequential terms. Okay, so it would be 2 over 10, right? which when we simplify is 1/5. So our common ratio is 1/5, which means that we can sum the infinite geometric sequence because it is between 0 and 1. Right, so when we plug it into our equation, the sum of this infinite geometric sequence is going to be equal to 10 divided by 1 minus 1/5. So when we simplify that, we get 10 divided by 4/5. And when we divide by a fraction, we're really multiplying by its reciprocal. So this is really 10 times 5/4, which is equal to 50/4, which is 25/2. I understand it, but it's just still a little confused on the infinite part. The infinite part just means that the sequence continues with no end. Okay, so we could continue this sequence of numbers all the way up and just continuing, right? So any number that you think of, we could go one beyond that, right? So the biggest number you can think of, right? Add one to it, and then add one to that, and then add one to that. It just keeps going, okay? But what's cool about these is that you can sum everything up and it converges to a certain number, right? So this sequence that we just found, or that we have, 10 to 2/5, 2 over 25, that's infinite. And yet the sum of all of those things is 25 over 2. And we can do that because the common ratio is less than 1. So I want to pause there. Are there questions about what you see on your screen? How did you get 1/5 to 4/5? 1 minus 1/5, right? So 1 is really 5/5. So 5/5 minus 1/5, that's 4/5. All right, I want to do one more because there's a couple of confusing ones in here, especially with fractions. Okay, In this example, it says find the sum of the infinite geometric series, right? So we're summing all these together infinitely, and we have to get a number. All right. Now, again, this part of the IXL is probably the most confusing because you don't actually have the sum and you can't pull numbers from it. But it's still the same process, right? You find a1, which is just the first term, so that's equal to 3. And then we need to find the common ratio. Because we know that it's geometric, we can just find the ratio between the first two terms. So 12/5 divided by 3, which is really equal to 12/5 times 1/3. So when we carry out that multiplication and then simplify, we get that the common ratio is 4/5. And then we just plug that stuff into our equation. So the sum is equal to 3, our first term, divided by 1 minus our common ratio. When we simplify that, we get 3 divided by 1/5. And then we get 15. Okay, and then we'll do one more. But before we do that, are there questions about this example? Okay, so the next kind of example I want to do involves the lower index and limit not being equal to 1 or 0. Okay, but the same process is true. Okay, we want to find the first term in this sequence from 3 to infinity, right? So if we plug in n is equal to 3, right, our first term of the sequence that we're summing, be 1/2 to the third power. Okay, because that's the first term that we're summing. Okay, so when we do that, we get 1/8. And our common ratio is just the thing attached to the exponent, so it's 1/2. So then we plug both of those into our equation. So the sum is equal to 1/8 divided by 1 minus 1/2. Then that's 1/8 over 1/2, which is equal to 1/8 times 2 over 1, which simplifies to 1/4. So again, this is an infinite geometric sequence that converges to 1/4. Okay, so questions about that example? Why is it converges again? It converges because our common ratio is between 0 and 1. So if our ratio was like 4 or something, it would diverge. But if it's something between 0 and 1, or the absolute value is between 0 and 1, it will always converge. All right. The last like 10 or so points has to do with converging or diverging. So all you really do, you'll be given something that looks like this. And it's basically going to ask the same thing. But the first question will be, does it diverge or converge? Okay. So the first thing you have to do is find the common ratio and interpret whether or not that means it converges or diverges. Again, if it's between 0 and 1, it converges. If it's greater than 1, it diverges. And then if it converges, it'll have another question, which will be, what is the sum? Which, again, is what we just did. Okay, so that's all the examples I wanted to go over. Again, it revolves around this equation. And we're just using that, okay? So I'll wait for any general questions here. And then after a couple of minutes, I'll close this and I'll start a meeting on Teams, which, again, you should be working. And if you have questions, I'll be there. All right. How come 1/2 to the third power is 1/8 and not 3/8? So that has to do with exponents. So 1/2 to the third is 1 to the third over 2 to the third. 1 times itself 3 times is just 1. 2 times itself 3 times is 8. All right, so again, general questions here. I'll be on Teams in a couple minutes. I'll leave this open for another, let's say, 2 minutes. and then I'll start a meeting. Okay, so I'll end this, and I will see you on Teams here in the next minute.